Swayam Prabha. Digital India. Educated India.
Yeah. We said basically that the inductance is always in the input side. So the inductance average value happens to be my input current average value as well. So IL average equal to IN average. So if I have that, then with this lossless converter relationship, I should be able to arrive at a relationship between I naught, IN and IL average. That's what we have done. Right? Okay. So buck-boost converter again has the same four components that we talked about. A switch, an inductor, a capacitor, a diode, right? All these things. So let us say this is my input voltage, Vin, right? Now we are going to have a switch here such that this is turned on and turned off. So this is my switch. Now I am going to have an inductance connected here, right? And this switch, when it is turned on, clearly it is short circuiting the inductance. Very similar to the boost action. Absolutely there is no difference. Whereas I am going to have a diode connected in this direction. Please note it is in the opposite direction. Right? And then I am going to have a capacitor here and a resistance here, which is the load. When the switch is on, I will have plus here and minus here. This is during when switch is on. Right? So it is storing the energy. When the switch is turned off, inductance has to give back its energy. So when it is giving back its energy, this is going to be minus and this is going to be plus during the off interval of the switch. So if it is like this, clearly the inductance is going to release, the current was flowing in the same direction, so the current would flow like this and like this. This is how the current is going to flow. So please note that in this particular case, I'm going to have plus here and minus here as far as the output voltage is concerned. Right? I will always have plus here and minus here. So it is actually inverted output. What I get as the output is in inverted polarity. Right? So this particular converter generally is known as an inverted output converter because the output voltage is going to be in reverse polarity, and in this particular case I am going to have essentially the input and output are hardly ever connected. Right? Initially when I am going to have the switch on, the diode is not going to be on. So the diode is the isolation that is existing between the input and output. And when I am turning off the switch is the isolation existing between the input and output. So it's completely isolated. The output is isolated from the input. They are not going to be connected together at all at any point in time. Right? So if I try to write the relationship, during T on, I am going to have it is very similar to the boost converter. There is hardly any difference between the boost converter equation and the buck converter equation as far as T on is concerned. So I am going to have V in times dt E is equal to L delta IL. This is going to be the equation. Right? Whereas if I try to look at it during T off, right? during T off, the inductance voltage is actually roughly equal to the output voltage, right? So I'm going to have actually V0 times 1 minus dt equal to L times delta IL. If I have to take care of the sign, I have to write delta IL is now in the negative direction. That's how you get V0 to be negative, right? Okay, because of delta IL being in the negative direction, because it is actually decreasing, I'm going to get essentially the inductance voltage is reversed, because of which I'm going to have the output voltage also reversed. So I would be able to write that V in times dt equal to minus V0 into 1 minus d times dt. So V0 equal to d by 1 minus d with a negative sign. The negative sign essentially indicates that the voltage is in the opposite polarity. The output voltage is in the opposite polarity as compared to the input voltage. So you don't even have to put the negative sign as long as you understand that the voltage is in the reverse polarity. Right? So let us try to now look at the waveforms for this converter again. So if I try to draw the waveforms for this converter, so let us say this is the reference axis I'm using and this is T. So I'm going to have maybe the inductance current is increasing like this and it is decreasing like this, and again it is increasing like this, decreasing like this, right? Somewhat like this. So this is the inductance current waveform, IL. So let me try to draw the time axis. So this is the time corresponding to, initially I have drawn on time to be small, but later on I have drawn on time to be somewhat larger. Doesn't matter anyway. So I hope you understand that I am not drawing very uniformly. That's it. That's the problem. Okay. So I am essentially looking at this as the inductance current. The inductance voltage is such that I am going to have V in coming up as the inductance voltage, which is corresponding to on time. So this is V in. And during off time, I'm going to get V naught. So if I am talking about the inductance stored energy, net inductance stored energy is 0, I will have to have these two areas. If I say A1 and A2, they have to be equal to each other. So this is actually VL. What we have drawn here is VL. Right? So we are going to have essentially this as V in and this as V naught. So these two areas have to be equal to each other. Right? Now, let us try to look at what is the kind of diode current that we are going to have. Diode conducts only during the input, only when the input switch is off. Otherwise, it's not going to conduct. So, let us try to draw the diode current. The diode current is only corresponding to the off interval. So, I am talking about this as T on and this as T off. Again, this is T on, this is T off. Right? So, I have to draw it corresponding to the off interval. So, I have to have something like this. Again, I have to have something like this. This is the diode current. This is the diode current. Right? And diode current, if I try to look at the average value, that will be my I naught. Right? So I have to draw I naught. somewhat like this. This is probably my I naught value. Please note again, this is averaged over a complete period T. Right? So it will be definitely less than even this value. It has to be less than that also because it is averaged over the entire period. So this is going to be I naught, from which I should be able to draw the capacitance current. Right? Capacitance current is whatever is the diode current minus this I naught value. Right? So I have to write ID equal to IC plus I naught. This is true in this particular case also. Right? So I have to write this as during wherever the diode current is 0, I'm going to have I naught. And when the diode current is there, I'm probably going to have something like this. And again, I will have something like this and then I naught. This is how it is going to be. Right? And if I again look at these areas, this is A and this is A dash, these two areas have to be equal to each other because the capacitance cannot retain any energy as such. So these two areas have to be equal. So here A1 equal to A2 and here it is A equal to A dash. So if I look at the capacitance voltage, yeah. Why is the diode current? See, diode current is, diode current average is not I naught. I should rather say that the output current average is I naught. But diode current, if I try to look at, over a cycle, the capacitance is discharging the energy for some time, but it is again accumulating the energy from diode only, ultimately. So, although it looks as though capacitance is providing the energy, right, to the load, when the diode is not conducting, ultimately even that energy is coming out of diode and inductance. Right? So I have to essentially average the diode current over the entire period, I will be able to get I naught. Otherwise I will not be getting I naught. Because the capacitance, whatever it is accumulating even for that short duration, that is from the diode. And that's what it is giving back to the load. So ultimately the diode current is giving the energy to the capacitance which it is providing to the load during the off interval. Right? So if I look at the diode current over the complete period, then that will give me the output currents average because of that. Because the diode is the one which is even providing for the capacitance. Right? Think about it, because capacitance, where will it get the energy from? It is getting from the inductance. But the inductance is essentially passing it through the diode. But I cannot say the inductance average current is same as I naught. No. In fact, inductance average current is neither I naught nor, I in. Neither of that. Because during initial condition, it is on interval, it is I in. Inductance current is I in. And off interval, it is I naught. So, you cannot really say that it is exactly same as I naught average or I in average. We'll have to calculate that also for getting L minimum. Okay? Fine. So, if I am looking at how really the capacitance voltage is increasing and decreasing, whenever I am getting a current from the diode which is charging the capacitor, I am going to probably have increase in the capacitance voltage. Whenever it is discharging to the load, it is going to decrease, and so on and so forth. This is how it will be. So this will be VC, whereas this will be IC. Right? It is quite easy to calculate the capacitance value. It is same as what you had in the other case, that is the boost converter. We said basically I naught is coming up, so I can write A dash is equal to whatever is C times delta V naught, which is delta Q. Which, so I can say capacitor design. What I am writing here is capacitor design. So capacitor is designed somewhat like this. Now I should be able to write this as, this is I naught, whatever is the value is I naught. So I naught multiplied by, this is during the on interval, dt. Right, I naught multiplied by dt. So which I can write this as V naught divided by R multiplied by dt. Right? So from which I can directly write delta V naught divided by V naught equal to D divided by R CF, which is same as that of the boost converter because it looks almost similar. There is hardly any difference between the two. Now we'll have to look at the inductance value, that is critical inductance value. So L critical. When we are looking at L critical, maybe we will have a higher variation in the current, so it will go something like this and then come down. It will go something like this and come down and so on. This is how it is going to be. So I'm going to have higher variation in the inductance current. So in this particular case, of course, I'm going to have delta IL equal to I max because it is touching 0. So whatever is the maximum amount of current, that is going to be same as delta IL because I max minus I minimum is 0. Right? So if I try to look at what is the average inductor current, let us try to get what is the average inductor current. I should say IL average is actually delta IL divided by 2, which is I max by 2 also. That's fine. Right? But how do I really equate this ultimately to I naught or IN? I have to look at that basically. So if I want actually I naught average to be calculated in terms of whatever is the value that I am getting for, the inductance current. If I want to interpret what is my I naught in terms of inductor current. So I need to essentially look at the current only during this duration, during the off duration. Because until on duration, the capacitance was giving out the current. But ultimately, even that is because of the inductance stored energy. So we are coming back to Tanai's question again. So whatever is your inductance current during the off interval, if I try to average it over the complete cycle, that will actually come out to be my I naught. So if I try to look at this current, so I should say IL average, if I try to look at it, I have to take the area of this triangle, whatever I have shaded, and I have to divide it by T. Right? So which means I have to write first of all half B is 1 minus D times T, H is I max or delta IL. Right? This has to be divided by T because it has to be averaged over the entire duration of the complete period. So I have to divide this by T. This will give me what is actually I naught. This will not be IL average, this will be actually I naught. Similarly, if I try to look at the complete area under that right angle triangle during on interval and then average it over the period, that will give me IN. Because IN is actually Same as whatever is the inductor current that is flowing only during the on interval. Right? During off interval, I am not having any In, but I have to average it over the entire period if I want In average. Same is the case with respect to the inductor current, because inductor current is the one which is providing the complete energy to the capacitor, as well as there is no other energy source. Right? All the energy, even inductance is accumulating, is from V in. So there is no other energy source. So if I call this as I naught, right? So I have to just write this as T and T are getting cancelled, and I have to say 1 minus D times delta IL divided by 2 is equal to I naught. So we are now trying to correlate whatever is the ripple that we are getting with that of I naught. Right? So we will have I naught equal to 1 minus D times delta IL by 2. That's what we are calling as I naught, which is actually V naught by R. Now we have to substitute for delta IL, probably in terms of V naught or V in, whichever is okay. So we can substitute for delta IL. Now in terms of, let us say V naught. V naught is here. So V naught into 1 minus D multiplied by T divided by L. So I can say V naught into 1 minus D multiplied by T, because of which 1 minus D square aega. Then I will have T and divided by 2L. So in which case I have to write this V naught and V naught I can cancel. This V naught and this V naught I can cancel. And L I can take it to the other side. So I will get L critical equal to, what is it? 1 minus D whole square multiplied by T, which I can take it down. So I can simply say 2F right? R. R on the top, right? Okay. So this is L critical value. See, this particular converter, because the input and output are completely isolated, the average I in and average I naught calculation becomes a little tricky as compared to what you get in the other converters. Other converters, at least you get I in as the inductor average current or I out as the average inductor current, but that doesn't happen in this particular case. So buck boost converter specifically find applications wherever we look at a huge range of variation of voltage in the DC supply, which has to be converted finally into a particular constant value at the output for whatever reason. Maybe even for battery charging application. Battery charging generally is done, with the help of a rectifier most of the times. But there are applications where it may be done from solar PV. So the output voltage, because it may vary, in a large range because of the temperature, you might require a buck boost converter in those cases to bring it back to whatever is the value that is acceptable by the battery ultimately. So these are very commonly used in solar PV applications. So far whatever we have seen, in all the cases we have assumed continuous conduction, right? At least critical conduction. We have never assumed that the inductor current can dwell at zero value for longer. So let us try to take one case, that is the buck converter case first, where we will look at discontinuous conduction. So buck converter